So last time we looked at lists and saw some simple functions on lists. So let's get some more practice in defining functions on lists. So recall that a list is a sequence of values of a uniform type, and the type of a list whose underlying values have type T is given as list of T, written with a square bracket around it. And all lists in Haskell are built up in a canonical way using the append operator : starting with the empty list. And because of this, we have a natural way to define functions on lists using structural induction. And we can use this pattern x:x's to decompose a non-empty list into its head and its tail in our inductive definitions. So now let us look at inductive definitions of some interesting functions on lists. So the built-in append operator denoted : attaches a value to a list on its left. So what if we want instead to attach a value on the right? So what if we wanted to append right? So if we append right to an empty list, okay, if I attach a value here, then I will get a list consisting of the single value, which of course is the same as x:, empty list. Okay, so append right in the base case just gives me a singleton list, and otherwise, right, it is inductive. So if I have a list y0 to yn minus 1, right, and if I try to attach an x on the right, then I can pretend that y0 is the head of the new list and attach it to the tail of this list. So here is the definition of the function. We call it append r. So append r takes a value, so the first argument is an integer, takes a list and returns a list. Right? So it is from int to list of int to list of int. So as we saw, the base case is if I want to append right a value x to an empty list, I just get the singleton list containing x. Right? So this is the base case. And if I want to append right to a non-empty list, I can pull this out and try to insert x into the y's. So I have the first element of the new list will be the original y, and then what follows will be the result of inductively or recursively appending x to the right of x, y's. Right? So this is again the same style that we saw before. Right? We have a base case and an inductive step. So a natural operation on lists is to take two lists and fuse them together. So let's call this function attach. So we want to take a function which takes two lists, supposing we take 3, 2 and 4, 6, 7, and we want to combine these into a single list 3, 2, 4, 6, 7. So we have to now, in such a function, we have to apply induction to one of the arguments. Okay? So let us just choose to apply induction to the first argument. So the first argument to the attach, so attach now takes two lists, right? So it takes a list of integers, it takes a second list of integers, and finally produces the attached list where both lists are combined. So if the first argument is empty, then there is nothing to attach. I just get back the second argument. So the base case says that attaching the empty list to any other list L just returns L. On the other hand, if I want to attach a non-empty list to L, I can pull out the head of X, then I can attach the X's to L using induction, and then I can stick back the X. Right? So that's precisely what this says. It says inductively attach X's to L. Now X's is smaller than x:: x's by 1, so it's a smaller list. So this function is inductively defined. And now I can use the : operator to stick the X back. So of course this is an extremely useful function. So it turns out that Haskell has a built-in operator ++, which does precisely this. So 3, 2 ++ 4, 6, 7 gives us 3, 2, 4, 6, 7. So what if we want to reverse a list, right? So we want to take a list such as 1, 2, 3, right? And we want to produce 3, 2, 1. So a natural way to do this by induction is to first, since we know how to extract the head, extract this, then we take what remains and reverse it, and then we put this back on the right hand side using append r or using ++. Right? So reverse takes a list of integers and returns a list of integers. If I have an empty list, reverse has nothing to do, so reverse of the empty list is just the empty list. If I want to reverse a non-empty list, then what I do is I decompose this X, I reverse the tail, and then I stick this X at the end using either plus plus, or we could use append r, which we wrote last time. Both would be equivalent. But since plus plus is more compact, we'll just use plus plus square bracket x. So this is saying that adding the value x at the end is the same as attaching the list containing the single element x. So our next function is one that checks whether a list is in ascending order, whether a list is sorted. Right? So we want, if we think of the values in the list, then it should be going up so it need not strictly go up. Right? So we could have a section where the values are equal and then it keeps going up. But when you go from left to right, the values must be in ascending order. We could never go down. Right? So since we are talking about ascending order, this is like checking if an array is sorted. Right? So anything which has 0 or 1 elements is by definition sorted because there is no comparison to make. Now if I have 2 elements, then I have to do something inductive. So it is sufficient to check that the first element is correctly ordered with respect to the second element, and then the rest of it is sorted. So this is precisely what this function says. It says that if we have 0 or 1 elements, then ascending is definitely true. So ascending takes a list of integers and produces true or false. So it's a list of int to bool. Right? So if it has no values or only one value, then ascending is trivially true. Otherwise, and now notice that if it has reached this point, then the pattern x colon ys makes sense because we have definitely at least 2 values in the list. And remember that this is a short form for x colon y colon ys, which in turn will go further in and so on. So I can decompose any number of levels provided that number of levels exists. Right? So this pattern will not be matched unless there are 2 values, but if there are 2 values, then the first value will come to x, the second value will come to y, and whatever remains, which may be empty, will go to the y's. So now the inductive definition of ascending says, check that the first 2 values are correctly ordered, that x is less than or equal to y, and that what remains after that is also sorted. So this will walk down. So for instance, if you want to check it, if I say 3, 4, 4 for instance, right? So the first thing we'll check, okay, 3 is less than or equal to 4, and now is 4, 4 sorted. So this will say, okay, 4 is less than or equal to 4, and is the single list 4 sorted. Now the singleton list will match the base case, and it will say okay. Right? But the interesting thing about this particular definition is that we can have a 2-level pattern like this, which allows us to access not just the first element, but the second element or even the third element. We can have a 3-level pattern. Provided the list has that many elements, we can individually name all those elements directly in the pattern. So here is a more interesting version of the previous thing. So supposing I want to check that the list either looks like this, that is the values keep going up and down, okay, or it looks like this, the values keep going down and up. So we want to check if a list of integers is alternating, so the values should strictly increase and decrease at alternate positions. As we have seen, there are 2 possibilities. It could start strictly increasing, so this is position 0, then position 1 is bigger, then position 2 smaller, 3 is bigger, and so on, or it could be other way around. Okay? At position 1 it goes down, and at 2 it goes up, at 3 it goes down, and so on. Okay? So let us look at the second case. Okay? So this should be reversed. Right? So if it starts in increasing order, I will say it is an up-down list. It goes up first, then it goes down. And if it starts in decreasing order, I will say it's a down-up list. It goes down, then it goes up. Now, if I cut off this list at this point, right? So it started as an up-down list. Then this position, the remaining part must be down-up, right? So that's the observation, that up-down and down-up are connected. Okay? So if I start an up-down list and I remove the head, the tail must be of the opposite type. Similarly, if I have a down-up list and remove the head, the tail must be of an opposite type. So this is an interesting definition because we will define up-down and down-up in terms of each other. So just let's look at the definition. So first of all, we say that a list is alternating if it is either of the form up-down or it is of the form down-up. Yeah? When is it up-down? When it goes up and then comes down. Right? So up-down and down-up, just like sorted, are trivial for lists which don't have at least 2 values. Okay? So if I have 1 value or 0 values, then both up-down and down-up will return true. On the other hand, if I have two values, then up down must start by going up. So I want x and then y, right? I want it to go up. So I want x less than equal to y. And now as we observed, once you go up, the remaining part must go down. So the next step must be down. So the list starting from y onwards will be going down and then up and then up. So this part will be down up. And symmetrically here, if I want to start going down, then I want that the first x is bigger than the second y. But then after this, it is up down. Okay? So these are what are called mutually recursive functions. Okay? So alternating says that the list must either be of the form up down or down up. Up down and down up both have their base cases, and then they are defined in terms of each other. The first position determines whether it's up or down, and then you reverse. Okay? So this is a kind of interesting mutually recursive function on lists. So Haskell, of course, like you would expect, has many built-in functions on lists. So some of the functions we have seen and some which we have defined are actually built-in functions. So head and tail we have seen. Length, sum and reverse we wrote, but actually they are built-in functions. So you can take a length of a list, sum of a list, reverse a list, and so on. Now, the opposite of head and tail is to decompose the other way. So remember that head and tail knock off the first element according to the colon and the remaining thing. Now, it may be that you want to knock off the last element. So then this is called the initial segment and this is called the last value. So there is a function init which returns everything except the last element. So if I have a 3-element list, it will return the first two. If I have a 1-element list, it will return empty because if I remove the last element, nothing is left. And last will be the value at the end. So last of this list is 3. Last of the list containing 2 is 2. Right? And once again, init and last will only work if the list has at least one value. So you cannot define init or last for an empty list. Sometimes you don't want the first or the last, but you want to break a list at some point. So supposing you have a list, you might want to take either the left hand part up to a certain position, or you might want the right hand point from a certain position onwards. So these are functions called take and drop. Take gives me the first n values. So I'll have n values here if I take. Okay? And drop will on the other hand give me these values. Right? If I drop the first n values, then I will get the n plus 1 value onwards. And take and drop will do the obvious thing. So if I try to take 0 values, I will get an empty list. If I try to take a negative number of values, if I take -5 values, I'll get an empty list. If I take more values than the list has, it will give me the entire list. So it's not going to actually worry about whether n is within the range 0 to n, length of the list -1 or not. And the same with drop. If I say drop -5 values, it will drop nothing. If I say drop everything, then it will give me an empty list. So the useful thing to remember is that between take and drop, there is no gap. So if I take n elements and I drop n elements, then every element either gets into the first part or the second part. So if I then combine them using my attach or concatenate operator, then I will get back the original list. So for any n, any value of n, okay, whether n is a sensible value or not, whether it's within the range 0 to length of list -1 or not, take nl plus drop nl is always equal to n. So just to exercise our skills in writing functions on this, let's try to define our own version of take. So remember that take must take a list, first a number and then a list and give me back a list. Right? So it takes an int, a list of int, and gives me back a list of int. So if I take any n values from an empty list, I get nothing. So an empty list, I cannot take anything because there's nothing to take. So for any n, my take n of the empty list is the empty list. Now if it is a non-empty list, I will use induction. I will go by cases on n. So if I'm taking no values, if I say 0 values are to be taken, then I get back the empty list. If I want to take n values, so I have x0, x1, this is my thing. Supposing I want to take k values from this, then the idea is I will take out this thing and then I will take k -1 values from what remains. Okay? So I pull out the first value and then I take one less value from the rest of the list. And remember that if n is very large, then at some point x will become empty and this will just return empty. And finally, we have a last case which takes care of negative n. Right? So it says if n is actually less than 0, I should give you nothing. So notice that actually these two cases are together. So I could have said n less than equal to 0 is equal to empty, and it would have done the same. Right? So we have seen a number of examples of functions on lists, and almost any interesting function that you write on a list will be defined using the structure of the list by induction. So something that we should think about is when we wrote length, right, we explicitly wrote a length for a list of integers. Now, if we wanted to write length for a list of float, or a list of bool, or a list of car, or a list of anything else, then it is clear that the function will do the same thing, right? It will just say it is 1 plus the length of the tail. It doesn't have to look at the values inside the list. So the type of the value inside the list is really irrelevant to length. Similarly, reverse. If I just want to reorder, it's just a structural property. I want to take if I have a bunch of boxes and I want to reverse a sequence of boxes, I don't need to look inside the box to find out what is there. I just need to move them around. On the other hand, the way we have written types for lists, we are forced to say that this is a list of int, or this is a list of float, or this is a list of car. So question to think about is, what would be a good way to assign a more generic notion of a type to functions like this, which don't actually need to look internally into the values, but just need to know the structure of the list.